Talking about the final project, actually we have 6 different topics for you. The first 2 will be accelerometer, the second one will be a seismometer. The difference is for accelerometer and seismometer for accelerometer we will use the this part as a sensing part because we have signal output here. So beyond this part there is no signal output, so we cannot use this part. So in order to have a high frequency response, so we need to increase the omega n. How to increase omega n? Because omega n equal to k over n, right? So you need to try to reduce the mass or increase the spring constant, okay? In order to have a larger dynamic range. The frequency response range, not dynamic range, frequency response range. But for seismometer, we are usually using this part because this part has output. This part does not give you output. So this part cannot be used. You can use this part. If you want to have a large the measuring portion, so in that case you need to decrease the omega 0 in seismometer. So in order to decrease this one, you need to increase the mass or decrease the spring constant. Okay, so that means in seismometer you need to use a huge proof mass. Okay, in order to increase the sensing region to reduce the natural frequency. So the basic difference of the design for seismometer and accelerometer. They are using a similar structure of the device, but the design idea is the opposite. Okay. Okay, this is for your reference. After understand the very difficult part of the dynamic situation of the beam. So now we are going to move on to the next topic. Okay. So next we are talking about when the whole system, the cantilever system, encounter acceleration from outside, what will be going on interiorly. Okay. So first of all, there will be the bending of the beam according to the bending moment exerted onto the beam. So when we separated the beam from the proof mass, so we will consider there are 2 actions when we have the bending of the beam. There will be one bending moment. Okay, the bending moment is from the original considered as the proof mass over here. Now has been separated from the beam. We are showing the beam only here. There's no proof mass. So the M0 is coming from the proof mass originally. Remember, the center of the proof mass, there are some distance between the center to the tip of the beam. So in that case, the proof mass will give a bending moment here. So not a bending moment here, but also will give a force at the tip. So in this case, the tip of the beam will feel 2 actions. One is a force, the other one is a bending moment on the beam. Okay, so after these 2 external bending moment or force applied onto the tip of the beam, so you will see the deflection of the beam. So there's an equation corresponding to the deflection corresponding to different distance to the base of the beam. Okay. So when we consider the balance for a small portion of the beam, the bending moment on the left-hand side will be balanced with the bending moment from the right-hand side. So if we consider this point as a balance point, so the bending moment will be similar to this one, and also the force times the distance here will be balanced with the mx, this one. Okay, so this equation will be developed later on, and you can see the final results of the bending moment close to the beam for different places. Okay, so now you got the bending moment here. So now we consider what kind of a curvature you will have at the local region. Okay, so the curvature. Okay, though means the radius of curvature. Okay, radius of curve. So 1 over dou means the curvature. That means how curved the structure it is. So the curvature will be proportional to the bending moment actually. So you have a large bending moment. That means at the local region, you will bend more and have a large curvature. Is more curve, okay? And the curvature will also inversely proportional to the Young's modulus. Young's modulus means the stiffness of the beam. If I have a higher stiffness of the beam, that means the beam is not easy to deflect. Okay, stronger, it's not easy to deflect. So the curvature will inversely proportional to the Young's modulus. This is a material property, okay? The other one is I means the momentum of inertia. Momentum inertia is a kind of a interesting idea. Most people don't understand it very well. Momentum inertia, that means how good the beam can be bent. If we have a large momentum inertia, that means the beam is not easy to bend. It can resist the bending. You can consider it like a mass. If I have a large mass, you give it a force, the acceleration will become small, right? The same thing applies here. If you have a larger momentum inertia, if you give it the same bending moment, the beam deflection will be small. Sounds like a large mass things. So you can consider the bending, momentum inertia I. That means the structure is a structure property. That's not a material property; it's a structure property. So you have a special design of a structure. The structure can resist the bending very well if you have a higher momentum inertia. Okay. So, for example, if you have a, can I borrow a ruler? Do anybody have a plastic ruler? Yes, thank you. The same material, right? Okay, but you design different structure. You have different momentum inertia. For example, if you bend the ruler in this direction, it's easy, right? Because all the material is at the center, become very thin structure. So the momentum inertia in this case is small. But the same structure, you turn it 90 degrees to upright. Now you bend it again. Is it easy or not? Not easy at all. Why? Because it increases a lot of momentum inertia. The I increase a lot because all the materials are far away from the center point. If you put all the material at the center point, the momentum inertia will be large. But you put the material far away from the center part, it becomes very difficult to bend, can resist the bending very, very well. So you have a higher momentum inertia. So for a square, so you see the cross section is a square cross section. So when we talk about the momentum inertia for this structure, the equation will be like this, the bottom one. The I equal to A cubic times B over 2. The A means the distance, the height. A means the height. B means the width. B means the width. Okay, thank you very much. Okay, if you have a beam structure like this, the A means the height, B means the width. So if you put the same material like the ruler, put more material on the A side instead of B side, you can have a larger momentum inertia. Exactly the same as I just showed you. We flip the beam into vertical direction, so it becomes very tough to bend, right? That because it increased the momentum inertia, become larger. Okay, that's the meaning of momentum inertia. So the momentum inertia is a structural property. It's not a material property. So finally, we can see the curvature is proportional to the bending moment from the outside, inversely proportional to the material property, the Young's modulus, and inversely proportional to the momentum inertia. So you have a large momentum inertia, you won't get a lot of curvature. Okay? Okay, and from calculus, you can see the curvature corresponding to the deflection of the beam. Okay? It's a very complex equation from the calculus, but we can make it simple, become the final equation round square y round x squared. Okay, when we have not that much deflection. Okay, so if the round y round x is smaller than 1, so we can take out the bottom one, become 0. So the bottom one will become 1. If you take out this term, and finally become this one. So this equation will become very simple. So when the curvature is look like this, corresponding to the structure shape change, and you can equate this equation with the previous one. So replace this one as a round square y round x, and you can have a new equation over here. So this equation is a second derivative equation, second order derivative equation. It's become very easy to solve. Okay, you just integrate twice, okay, the equation, and put it into the boundary condition, and so you can finally get a very simple result. So remember the bending moment on the beam at a different direction position will be two terms working together. One is the force working on the tip of the beam. The other one is the moment from the proof mass. So these two will finally form the bending moment across the whole area. So now we consider if the formula like this, from the tip, x means the position of the beam. Okay, when x equal to 0, the position will be at the base of the beam, right? When x equal to L, that means at the tip of the beam, right? Okay, so consider this equation. So which part of the beam will encounter the maxima bending moment from this equation? Is it at the tip, at the center, or at the base? At the base means x equals to 0. At the center means x equal to L over 2. At the tip means x equal to L. So which one? The base, center, or tip? It gives me three choices. It's important because later we want to design a sensor. So this is the base. X equals to 0. This is the center. It's a tip. So the question is, which part you can find out the maxima bending moment? Look into the equation. Yeah, equation will tell you the solution. At the base, center, or tip? Choose one. Okay? You think it's on the base? Please raise your hand. Okay, like 10, 12 people. Okay, thank you. Center? Tip? Okay, several. So, yeah, thank you. So, how about the rest of people? You want to give out the course? You don't want to answer the question? Okay, actually, we look into the equation. The equation is mx equal to, right? So mathematically, when you put the x equal to 0, you got the maxima, right? Right? Okay, why? You need to consider this physically, otherwise you never remember. Why? It's important because later on we want to put our sensor onto the beam, on top of the beam, on the surface of the beam. So you need to decide which part you need to put your sensor on. You want to put your sensor on the tip, at the center, or at the base. That depends on which part gives you maximum signal, right? Okay, from the equation, easy to understand. At the base, you got the maxima bending moment, but not easy to understand. But you need to consider you have a bending moment and also a force applied on the tip of the beam. So for the bending moment, if you consider a beam the balance of the bending moment at this position, okay, so the mx will be equal to m0 plus f times the arm. The arm will be the length here. Okay. So at which position the arm length will be the largest? You understand? The bending moment here will be the moment 0 plus F times L minus X, the distance here. Okay. So at which position the arm length will be the largest? At the base, right? Yeah. At the base, you have the whole length of the beam, right? 0 deduction, all the beam as your arm. 就是你的力臂会是最长的。听懂了 ？Okay. Thank you. So in that case, you got the largest bending moment. So you got the largest, okay, bending moment at the end here. Okay. So the bending moment will be proportional to the what kind of parameter, important parameter? 1 over rho. What is 1 over rho? The curvature. The curvature. Okay. So we're talking about curvature. So here you got the large curvature here, but at the tip, do you get any curvature? 0 curvature. At the tip, no curvature. The curvature means, okay, let me draw a figure to make you understand this in more detail. Otherwise, if you only memorize the equation, you never got the physical meaning. Think of this. You have a bending like this. So you draw the curvature along this surface. You find a small curve. So smaller circle means a larger curvature. Okay. So here you got the largest curvature, right? That means you got a small circle here, the radius of circle. Rho base, rho 1, rho 2, rho 3, and so on. So you will see the circle become larger and larger when you draw the circle according to the curvature along this surface. Okay? So the small circle means it's a higher curvature, highest curvature. So you got a lot of bending here. To give it a small circle, that means a higher curvature. 就是比较大的曲率，弯曲的很厉害的意思，在这个地方。这边弯曲不厉害，这边弯曲的很厉害。Okay? But at the tip, the curvature equal to 0. What does that mean? Yeah, curvature equals 0 means there's no bending moment. Bending moment equal to 0. Okay? If you don't consider this one, okay? Consider only this one. There will be no curvature. But if you consider N0, still have some curvature over there. Yeah. So larger circle means a smaller, larger, yeah, that means a smaller curvature. Yeah. So the bending is not that severe. But if you have a smaller circle, that means a large curvature. It's bending very serious here. So we want to put a sensor. You want to put a sensor here or here? Which one? 1 or 2? You like to put it here or here? Which one will give you more sensitivity? If you think it's a 1, please raise your hand. If you want to put a sensor, yes. Oh, curvature. You want to detect the curvature, the displacement later on. Okay. Okay. Which one you want to put? You want to put it 1 or 2? 2. 2. Is everybody thinking 1 is a correct position? No. Because of 1, okay, you see 1 have a lot of diffraction, large diffraction, but on the surface, there are not much curvature. The curvature means if you have a large curvature, that means that you have a more extension of the material Okay, there. So later on, we are going to measure the displacement, okay, on the surface. So more curvature means give you more extension of the material. They will give you more signal. Is it clear? OK， 越弯曲的地方，它的材料扩张越大，扩张越大，它变形越大，我们量到的讯号也会越强。所以你要放 sensor， 要放在讯号最强，也就是说它变形量最大的地方。变形量最大的地方就是最弯曲的地方，变形才会大。越直的地方怎么会有变形？都不会变形。OK， 好，虽然整个鬓的偏折这边是最大的。但是它的 tip 的所受的这个 bending moment 是最小的，所以我们 sensor 不是放在 deflection 最大的地方，是放在最弯曲的地方，要记得，这个常常会搞错。当然，这是对于用那个压阻式的，是这样子放。但是如果你的 sensing method 是量测，像电容方式是量测距离的话，那你当然要放在 tip 的地方，它距离变化大，就看得清楚。但是对压阻式的话，它量测的是 strain， 量测是变形量，所以它要放在这个地方。OK？ Yeah. So I'm thinking, because later on we are going to using piezoresistive type of sensor. Piezoresistive sensor is sensitive to the strain of the material, the structure. Okay. So you need to find out which part gives you the largest strain. So here, this part gives you the largest strain than the other part because I have a higher curvature. That means I give a lot of more extension of the material. So this part can give you more displacement for measurement, more strain. Okay, for measurement than the other part. So piezoresistive sensor, it would be better to put it here than here. However, if you want to use the capacitive type sensor, the capacitive sensor is by doing the measurement by using the distance change. Okay, so for capacitive type sensor, it may be better to put a sensor here instead of here because I have more deflection here. The distance change here is much more. But for distortion, material structure distortion, the strain will be larger here than here for piezoresistive type sensor. Is it clear? For different type of sensor, you need to put different places. Okay.